Welcome back to the Explainer, everyone. Look, if you're an advanced machine learning student stressing over finals, or maybe you're prepping for one of those famously grueling technical interviews at a top tech firm, you are exactly where you need to be. Today, we're tackling a beast of a topic. We're going to untangle two concepts that literally constantly trip people up: speaker adaptive training, or SAT, and FMLAR. We'll break down exactly what they are, how they interact, and why they're absolutely essential for modern acoustic modeling. By the end of this, you'll have the precise clarity you need to absolutely crush those exam questions. Let's get right into it.
To keep things manageable, here's our game plan for today. First, the blurry average problem. Then, the SAT versus MLLR analogy. Third, the iterative loop. Fourth, the try 3B stage gains. Fifth, the two-pass decoding challenge. And finally, we'll wrap up with the 60-second pitch.
All right, section 1, the blurry average problem. Or, in other words, why your Centro GMMs are failing. Picture this. You're sitting right across from a senior engineer in an interview, and they slide this exact question your way. Why are your Centro GMMs failing before adaptation? It's a classic for a reason. Well, the issue actually isn't a lack of training data. The real problem is that your model is being forced to absorb way too much variation all at the exact same time. Let's look at what that actually means in practice.
Think about an unadapted model compared to an adapted one. Without SAT, your standard Sonone GMM is essentially pulling double duty. It's trying to model the phonetic identity, what sound is actually being spoken. But it's also trying to model the speaker characteristics, meaning who is speaking. Is the speaker male, female, a kid? What's their vocal tract length? Do they have a heavy accent? When you force one single statistical model to juggle all of that massive variance at once, it just spreads out. It turns into this blurry average over all speakers, and that completely tanks your transcription accuracy. But when we adapt the GMM, we strip all that speaker identity away. The model gets to focus strictly on the phonetics, which gives us these incredibly tight, precise statistical distributions.
Moving on to section 2, the SAT versus FMLR analogy. The recipe versus the ingredient. So, how do we actually get from a blurry model to a tight one? Well, first we have to avoid the absolute biggest trap in ML interviews, which is mixing up the training procedure with the mathematical transform itself. Seriously, burn this distinction into your brain right now. SAT, speaker adaptive training, is a training procedure. It is not a transform. FMLR, on the other hand, is the feature transform. It's kind of like cooking, right? SAT is the entire recipe. It's the step-by-step method you're following in the kitchen. FMLR is just one specific ingredient that your recipe calls for. So the role of SAT is to use that FMLR ingredient inside a repetitive training loop. And the role of FMLR itself is just to map a particular speaker's voice into a normalized canonical space. Don't ever mix those two up.
To really drive that home, let's zoom in on that specific ingredient. FMLLR stands for Feature Maximum Likelihood Linear Regression. It sounds like a mouthful, but strictly speaking, it's really just this simple math equation, an affine transform where the adapted observation vector equals matrix A times the original observation vector plus bias vector B. That's literally it. It's just the math we use to shift and scale a speaker's acoustic features so that they sound like some generic, standardized speaker in our canonical space. Just math.
All right, section 3, the iterative training loop. Let's see how we actually train these GMMs.
So now that we've got our mathematical ingredient, how do we actually use it in the SAT recipe? Well, here is the 4-step iterative training loop that really defines speaker adaptive training. Step 1, for every single speaker in your training data, you estimate their specific FMLR transform. Basically, use maximum likelihood to find that unique A matrix and B vector that best maps their voice to the current model. Step 2, you apply it, pushing their features into that canonical space we talked about. Step 3, and honestly, this is where the magic happens, you retrain all your Sonone GMMs on these newly adapted features. Since the features are now speaker normalized, the GMMs finally get to learn just the phonetics. And step 4, you iterate. You just repeat the whole process until convergence. Why? Because better, tighter GMMs will let you calculate even better FMLR estimates on the next pass, which then creates even better GMMs. It's a beautiful, self-improving loop.
Section 4, Tree Stage Performance Gains. Let's look at the actual results of all this adaptation. Now, running this loop is computationally expensive, right? So why do we even bother doing it, specifically at the Try3B stage of acoustic model training? Well, the immediate payoff of SAT is that those wide overlapping statistical distributions become incredibly tight and highly discriminative. Because we shoved all that messy variance, the gender, the vocal tract blank, the accents, into the per-speaker FMLR transforms, the acoustic model doesn't have to waste its capacity modeling human identity anymore. It gets to spend 100% of its predictive power just distinguishing between phonetic sounds.
And let me tell you, the payoff for that hyperfocus is absolutely massive. Usually, by applying SAT at the Try3B stage, we're talking about a solid 15 to 20% relative reduction in word error rate compared to the earlier Try2B stage. In the world of speech recognition, a 15 to 20% drop is huge. It is a total game changer. It's literally the difference between a system that totally fails to understand you, especially in those noisy everyday environments where background sound just adds so much messy variance, and a system that feels basically magically accurate, even with all that noise.
That brings us to Section 5, the two-pass decoding challenge, SAT at test time.
Of course, all this incredible accuracy doesn't exactly come for free. The big logistical headache engineers have to deal with here is that a SAT-trained model strictly expects to see adapted canonical features. It literally forgets how to process raw, unadapted speech. But think about test time. When a brand new user speaks into the microphone, their specific MMLR transform is completely unknown to us. So engineers are forced to implement a pretty heavy computational lift, two-pass decoding. Here's how it works. Pass 1, you use a simpler, unadapted model to just do a quick, rough transcription, giving you a first-pass lattice. You take that rough guess and you use it to estimate the new user's MMLR transform. Then, in Pass 2, you apply that transform to their I/O and redecode the whole thing using your highly accurate SAT model. Yes, it literally doubles the decoding effort. But hey, that's the price of admission for those massive accuracy gains.
All right, finally, Section 6, the 60-second pitch, your ultimate exam cramp.
Okay, we've covered the math, we've covered the loop, and we've covered the deployment challenge. Now, if an interviewer asks you to explain SAT, this is exactly what you tell them. Ready? SAT, or Speaker Adaptive Training, is a training procedure that removes speaker variability so the acoustic model can focus entirely on phonetics. Without it, your Senon GMMs waste their capacity modeling both the sound and the speaker, which turns into a highly inaccurate blurry average. To fix it, SAT alternates two key steps in a loop. First, it estimates each training speaker's FMLR transform to map their features into a canonical space. And second, it retrains the GMMs on those adapted features, iterating until convergence. The absolutely vital distinction is that FMLR is just the mathematical transform, while SAT is the overall recipe that uses it. This gives us tighter, more discriminative models and drops our word error rate by a massive 15 to 20%. But because a new speaker's transform is unknown at test time, deploying a SAT model strictly requires a two-pass decoding system to estimate that transform before the final decoding.
Boom, you say that and I guarantee you've got the job. So, the final question I have for you is, are you ready to adapt your own training? We've untangled the blurry average, we've separated the recipe from the ingredient, and we've mapped out the real-world engineering constraints. Keep these concepts front and center as you prep for your exams. Always remember the difference between the procedure and the math, and you are going to absolutely crush it. Thanks for hanging out with me for this explainer, and I'll catch you in the next one.